And there is one more thing with every single object, and it's at the top. It's called sync block address. Wherever you call the hash code method for the object or try to log the object, those information must be stored somewhere. And this is where it's stored in sync block address. It contains multiple things. It can store hash code. It can store the so-called thin sync block, where it just contains the information that the object is logged. It can be a pointer to some different metadata describing what threads are waiting for the object. So there can be a lot stored just in this one sync block. Even though it's typically on 32-bit architecture, it is 4 bytes long only. And what is also interesting here is that our managed pointer, this thing on the left side, var_o, does not point to the beginning of the object. It points to the middle of the object, to this RTTI address. So if we want to take a look at the object, which we do pretty often, to call any method, to do anything with the object, we probably need something from the metadata. So that's why this pointer points to RTTI address, not to the sync block. Sync block is before the object, and we need to remember about this because soon we'll be doing some stuff with this thing. Okay, any questions to this? If not, then let's continue. I told you that we are going to allocate the reference type on the stack. And the first thing we are going to do is actually we'll cheat a little. We won't allocate the object directly on the stack. We'll just copy this object from the heap to the stack. This will be the first demo. In some later demo, we will implement the correct allocator, which will allocate the object directly on the stack or any place we choose. However, for the first demo, we will go some different path. And well, the question is, how do we do this? There are two things which we need to handle to do it. First thing is how do we actually copy the object on the stack? And second thing, how do we get a reference at this managed pointer to this created object, which is on the stack, which will be on the stack? And the answer is we'll use this __ makeref keyword, which is in C# since the very beginning, like I said. And this gives us something which is called typed reference. It's a different type of reference which is actually pointing to the reference. So we'll have object, reference pointing to the object, and finally typed reference pointing to the reference, pointing to the object. So it will be like two-star programmers. And this typed reference gives us this beautiful magical thing that we can actually get the address of this typed reference. So we'll have pointer to pointer to pointer to object. Why do we do this, all of these things? Because if you ever played with unsafe context, you cannot take the pointer to the object. You cannot have object star. You can have int star, you can have double star, whatever, but you cannot have the pointer to the object itself. By using typed reference, we can get the pointer to the pointer, and finally get to the address of this object. We could do it a little easier just with Marshall class. However, at the end, we need a pointer to the reference, so we can modify this reference and switch it from the heap to the stack. This will be probably when you see the code, it will be a little more clear. Okay, makeref. Why is there ever in C# this keyword? The answer is, before we had .NET 2.0, we didn't have generics, yes? If we were to implement a method accepting anything, either value type or reference type, we had to use objects, so we had boxing, which was slow. However, with makeref and with typed reference, we could just pass the pointer to some data, so we could avoid the boxing and the performance penalty. And if you take a look, like I said, answering this one question, if you take a look at span of T and memory of T, those are exactly the same concepts, but now in safe context. You don't need to resort to unsafe context or do some magical stuff on the pointers. You can just use managed types which do exactly the same. So we have makeref, which will give us the typed reference thing, and there is also another keyword called refValue, which does the opposite. Yes, so we have typed reference, then we get the reference to the object. We use those two keywords to actually do the whole magic stuff. So just to visualize what we are going to do with all those things, we start with new object. This is like the object stored on the heap. we have the reference to it. Yeah, reference is just like the address is just a number pointing to the location in memory. Then we create typed reference pointing to this reference. And finally, we get the address of typed reference. So we have a pointer to pointer to pointer to object. And then by casting it to int pointer, doing some nice calculations, some black magic, we can actually read the bytes of the object, copy it, write it wherever we like. This is the idea. Any questions? No? Okay, let's go. We actually, last thing before we get down to the code is how do we verify whether we did what we wanted to do? Well, the answer is we'll first use WinDebug to actually see the raw bytes of memory. However, there is a very simple way to do it. Some GC facts to the rescue. As we know in .NET Framework or .NET Core, there are 3 generations, 0, 1, and 2. And there is something called large object heap, which stores the objects bigger than 85,000 bytes. Yes? Trivia here. What else is stored on large object heap in .NET Framework?
Strings?
No, strings are not. The answer is, and it was changed in .NET Core, wherever you allocate the array of doubles, which is long at least 1,000 in size. At least 1,000 doubles in the array, that array is stored on large object heap. This was changed in .NET Core, so it's not the case anymore. Okay, and large object heap is stored, like generation of the objects stored in large object heap is 2, generation 2. Whenever we ask the object in GC in which generation is the object, it is in object 2. Yes?
So you mentioned this really puzzling fact. Do you have any explanation why this double thing, just one sentence?
Just these things? If we would, like I said, we want to verify that we are doing...
What's up this 1,000 long...
this thing.
Yeah.
I don't know the correct explanation. I know this thing from some Microsoft conference, and the explanation provided there was that there was some internal analysis that 1,000, that array of 1,000 doubles performs better when it's stored on large object heap, because people are probably doing some math calculations, so it avoids reallocation, etc. Don't know the answer. It does not convince me either. But yeah, this is how it goes. Yes.
On the previous slide, like you have pointer to pointer, and like how do you protect the array boundaries? Yeah, the last on the last object, last
This
box.
box.
Yeah.
And the question?
Yes. And the question is, how do you protect the array boundaries? Like, is there like once you have reference to this location, you can manipulate that to go and point to a different
Yes.
location. So how do you protect?
The thing is, I'm not going to protect anything here, as it's said by the word unsafe. The thing I'm going to do is, if I have this pointer, yes, I can indirectly figure out where this field is. I can read it. So then, I can read this pointer and go here, and go here. And the trick is, when I can read this thing, I can copy it to the stack and then modify the address here to have reference pointing to different place. This is the idea. Cool. Any other questions? If not, then I have a question for you. When we finally copy this object to the stack, you know there is a method gc.generation, something like this, which tells you in which generation is some object stored. The question is, in what generation will be the object stored on the stack? Just something to consider before we get to the code. Okay. So this is the code which we will be working on. So we have a simple class called Coco, which has just one field, one method which is non-virtual, one virtual method, and some destructor. Yes? What I'm going to do is I'm going to first allocate this object on the heap, then copy it to the stack, and then verify whether this object behaves in gentle manner. I mean, whether we can read the field, modify it, call methods, log this object, whether we can deallocate this object correctly, whether we can use reflection with it. Everything what you could imagine, what you could do with like normal normal instance, I would like to do it with this object allocated on the stack. So what we do first, we allocate some object. This lands on the stack, on the heap, sorry, and it has field set to value 5. Yes, this is just an integer field. Then we start our unsafe block, and we allocate some of the memory on the stack. We use stack alloc here. We could as well just allocate some big structure with enough integers, or just allocate raw integers, etc. And we fill this memory with value bad food. Yes, we should have 10 bad food integers on the stack. As we will see in a moment, we will use WinDebug to actually verify that we are taking a look at the correct place in the memory. Then we do our magic. We use __ makeref to create a typed reference. If you would have resharper installed, it would make this makeref in red, because resharper does not know this keyword. And then we do this magic as I described on the slide. Yes. So we first cast the typed reference we get the pointer to typed reference, cast it to pointer to integer, get its value, cast it again, subtract 4 because sync block is before the object, before actually the place that the reference points to, and finally we get nice pointer to the object. And what I'm doing first is I print out the type handle, this tag showing the type of the object. And we will verify that what I'm printing here is actually the same what we'll see in WinDebug. And this is like the first part, and then we copy the object, but we'll get to that. Okay, so first let me run this application. Okay. It printed something. Let's now attach WinDebug to this. Okay. Quick question: who knows SOS plugin to WinDebug? Who knows WinDebug? Hands up. Cool. So a few words before we get to the details. If you ever want to debug the application, whether it's .NET application or any other application, you need to have a support of the platform on which you are running this application. If this is .NET application, which is just a binary on Windows, you need to have a support from the Windows operating system. If this is Java application, you need to have some help from the JVM implementation. Yes? That's why in Windows itself there is a debugging engine. The same debugging engine which we are using when we are debugging something in Visual Studio. It is just a nice fancy UI for the debugging engine which is stored in Windows. So there are different UIs for this debugging engine, and WinDebug is one of them. This application is basically very useful for you when you try to debug something on the production. You probably do not want to install Visual Studio on your production host. So that's why you just copy this one binary to the production host, and you can have exactly the same experience as in Visual Studio. And there is one more thing in WinDebug. There is a plugin called SOS, which is Son of Strike. This is a plugin which is distributed with every CLR implementation, with .NET Framework, with .NET Core, with Silverlight, etc. And this is plugin which is compiled against the internals of the .NET. So if you want to read like the internal structure of objects on the heap, or examine the logs in the process, you need to know the structure of them, because it can change with every .NET Framework version, etc. Yes? So that's why you need to have this plugin, because it can read all those things for you. And it also gives you some of the nice commands to read the memory, etc. The thing is, you cannot use SOS in Visual Studio. It was possible in like Visual 2010. Later it was dropped, so you cannot load SOS anymore in Visual Studio. That's why we are using WinDebug to do it. Okay, so what I did here is I just attached to the application which is running underneath. And first thing I wanna do is, the question is whether you can see it, whether this is big enough. First thing I wanna do is too big? Okay, first thing I'm going to do is I will just load the SOS matching the CLR module I have already loaded in the application. And one more thing here, SOS, which is Son of Strike. One might ask, what is strike then? And a little of history of .NET background. CLR code name in the beginning was Lightning, and the plugin that CLR team wrote for themselves to examine like the memory internals was called Strike. It was a little not that nice, not that easy to use, so they rewrote this plugin and are now distributing it as a Son of Strike. There is also Son of Strike Extended, which is a plugin for a plugin, because you can write plugins for WinDebug. So it's like a wheel of time. Anyway, we just loaded the SOS. First, we are going to do now is I am switching threads to the thread I'm running on, because if you would see the thread in this application, there are a lot of them. And what I'm going to do now is I want to see what do I have on the stack. Like this command clr stack -a-i, it shows me all the details of the things I have on a stack. And if we take a look into the code, I am here in this line console read line. So you can see if we go like high enough, we started in the main, there is a read line, there are some other methods underneath the read line, implementation details, etc. You can see all of those. What is interesting here is we have our variables and we have our address of the stack frame for this method. So as you can see, I have two variables here, heap poco and original poco. This is heap poco and original poco points to the same object. Why I have two references to the same object? As I said, we will be modifying this reference and I don't want to lose this original object on the heap. That's why I copy it to the another reference. And also, like I said, yes, question.
Do you have this code somewhere so we can download it for them?
It is on my blog. Yes, I cannot give you like a link right away to download it right now. Cool, so we allocated some memory on the stack and filled it with bad food values. So let's see this. There is a command dd, and as you can see, it shows me the memory for this given address. And you can see we have 10 bad foods here. So those are the 10 integers which we allocated. And finally, we are going to copy the object into those 3 bytes. This is like our target. What's more? We printed out here the value of the of this in this tag describing the object. If we would like to dump this object, there is dump object. You can see that method table ends with db4, db4. Yeah, this is the same value. So we can see that we are reading the correct bytes of memory. And as you can see, value 5 is here as we specified it in this line. Yes, it looks like we are in good position. We are looking at the correct memory addresses. So let's go. Okay, let's go. And I'm hitting enter here. Okay, what we got here is this code executed, which read three integers of the object. Why 3? We have one field, which is integer. We have one single block, which is another integer. And finally, we have one integer describing the object type, this type handle, class, whatever you call it. So those are 3 integers, which I'm copying. First, I'm reading them, and finally, I'm writing to this array allocated on the stack. Yes? And also, I am like explaining, writing here what I copied. So now, what we want to do is we want to break into the application and switch the thread again. And CLR stack, and as you can see, we have the same address. Nothing has changed. Yep, and those are the bytes on the stack which we allocated. Initially, there were 10 bad food integers. Right now, we can see that 3 of them have changed. It looks like we are copying the bytes into the correct place. And the last thing we are going to do is we already now we have copied the object from the heap to the stack. Now what we need to do is we need to fix our reference so it points to the correct place. So what we are going to do is we are getting the address of second integer from the array allocated on the stack, do some black magic with typed reference, and finally like modify the reference which typed reference points to. We could also then we can retrieve then the reference to the object on the stack in one of the 2 ways. First, we can use this ref value keyword which I shown on the slides, But as I said, we just modified the reference. So this is basically the same if we would just use this heap auto reference later in this code. Okay, so let's run our application. It says that it's set reference to the stack, so we can now break. And what do we expect to see now? If we take a look at it, we can see that our two references, which were originally pointing to the same object, right now they point to different locations in memory. And also this heap auto, as I said, we modified it to point to the object on the stack. This address is, well, very close to this one. It's actually 4 bytes later because of this sync block, which is before the object. Any questions to this? If not, then we can actually start playing with our object. So first what I'm going to do is I call method which is non-virtual, just a method which is does not require binding in the runtime. And as you can see, yes, object on the heap, object on the stack, they have exactly the same value. Then I modify object on the heap and object on the stack and print out the values. I can as well modify the object on the stack just by modifying the value in this array which is allocated on the stack. Yes? So here I modify this value to 333 and print it here. So we can see that whenever we call methods, we modify the field, it works. Then what we are going to do is we want to execute some method, a virtual method which requires polymorphism, and as you can see, works as well. Finally, display object types. So we want to check whether the reflection works correctly against our object, and it does. And finally, the trivia which I asked before.